In this class, we are going to discuss about the numericals and a parallel operation of a alternator. Two single phase generators operated in parallel and a load impedance of Z ohms. The EMF induced in each generator E1 and E2 and their synchronous impedance are Z1 and Z2. Deduce the terminal voltage in terms of EMFs and internal admittances. Determine the terminal voltage and kW output of each machine if E1 equal to 100 volts, E2 equal to 110 volts, Z equal to 3 plus J3, Z1 equal to Z2 equal to 0.2 plus J1 ohms. Z is nothing but a load impedance. This is the formula to find out the terminal voltage in terms of a induced voltage in alternator as well as a internal impedance of a each generator. E1 by Z1 plus E2 by Z2 divided by 1 by Z1 plus 1 by Z2. 1 by Z1 you can write it as a Y1, nothing but admittance. The same manner, E1 Y1 plus E2 Y2 divided by Y1 plus Y2 plus Y, where Y is nothing but a load admittance. Now we are finding the admittance of each generator. Y1 equal to 1 by Z1, that is equal to 1 by 0.2 plus J1, we are getting this value. The same manner, load admittance Y equal to 1 by ZL, substitute the values, we are getting the 0.12 minus J 0.16. In this numerical, it is given that Z1 equal to Z2, so Y1 equal to Y2. So in this formula, you substitute the values of E1 Y1, E2 Y2, Y1 plus Y2 plus Y, we are getting the 96 minus J 3.87 ohms. If we keep in a polar form, 96.08 at angle minus 2.31 degrees. Current supplied by the first generator I1 equal to E1 minus terminal voltage divided by Z1. Substitute the values, we are getting the 5.457 at angle minus 34.64 degrees. Current supplied by the second generator I2 equal to E2 minus V by Z2, that is equal to 110 minus again terminal voltage divided by the impedance of a second generator, we are getting the value of 14.25 at angle minus 63.24 degrees. Power supplied by the generator 1 equal to V star into I1, nothing but a complex conjugate of a voltage 96.08 at angle plus 2.31 degrees. This is the complex conjugate for this one into I1, nothing but this current, we are getting the power 443 watts. The same manner we can find out the power supplied by the second generator V star IT equal to 96.08 at angle plus 2.31 degrees into current supplied by the second generator, we are getting the 664.8 watts. Now we are going to take up the second numerical. A 3 MVA 6-pole alternator runs at a 1000 RPM on 3.3 kV bus bar. The synchronous reactance is 25%. Calculate the synchronizing power and torque for mechanical degree of displacement when the alternator is supplying at a full load of 0.8 power factor lagging. So first of all, you have to find out the per phase voltage. The per phase voltage equal to line voltage divided by the root 3, we are getting the 1905. Full load current, this power divided by root 3 VL, we are getting the 525 amperes. Synchronous reactance equal to voltage drop across a synchronous reactance at a full load divided by V, that is equal to 525 into XS divided by the 1905, nothing but a voltage rating, this one equal to 0.25, because in the numerical it is given the 25%. So from this expression, if you find the value of XS, you are getting the 0.9074 ohms. The power factor in the numerical it is given cos pi equal to 0.8, so pi equal to 36.86 degrees. So the current we can write it as a 525 at angle minus 36.86 degrees. This is the phasor diagram. This is the V. Current lags the voltage by 36.86 degrees. In this numerical we neglected the resistance of a alternator. So perpendicular to the I, add the IA axis, this phasor, we are getting the E. The angle between the E and V, we are getting the 9.87 degrees. Now we are going to find out E. We know the relation for the E. E equal to V plus J I into Xs. Substitute all the values. We are getting the 2224 at angle 9.87 degrees. Nothing but this is the angle between the voltage V and E. That's why here we have taken the 9.87 degrees. The synchronizing power will be existing in alternator only when if there is a disturbance in a induced voltage. See here in the numerical it is given that the torque for mechanical degree of displacement. The rotor displacement delta in electrical degrees equal to delta in mechanical degrees into P by 2. So in mechanical degrees if we take a 1, 6 by 2, in electrical degrees that is a 3 degrees, in radians we are getting the 0.05236. Nothing but we are giving a disturbance of 3 degrees from E to E1 dash. Then the synchronizing power will be existing in a machine which brings the stator flux or rotor speed or the constant. Now this much of angle. Now synchronized power PSY that is equal to 3 delta EV by XS. Substitute all the values. Here you take the cos of angle between the E and V. Finally you are getting the 722.563 kilowatt. Synchronizing torque equal to this power divided by the angular synchronous speed. We are getting the value 6900 Newton meter. Now come to the third numerical. A 750 kVA 11 kV 4 pole 3 phase alternator has a resistance of 1.4 ohm per phase. Synchronous reactance 30 ohms per phase. Calculate the synchronizing power per mechanical degree displacement for full load for 0.8 power factor lagging at a terminal voltage of 11 kV. First of all, you have to find out the per phase voltage. You are getting the 6351 volts. Next, full load current. Full load current equal to power divided by the root 3 VL. You are getting the 39.36 amperes. Synchronous impedance is given. ZS equal to 1.4 plus J 30 ohms. Next, mechanical degrees. Delta in electrical degrees equal to delta in mechanical degrees into number of poles divided by 2. So here if you take the 1 degree in mechanical means you are getting the 2 degrees. If you convert it into radians that you are getting the pi by 90. Now you are going to find the induced voltage. Induced voltage equal to E equal to V plus I into Zs. In place of Zs you take this value. Substitute all the values, you simplify, and finally if you keep that value in polar form, you are getting the 7162 at angle 7.31 degrees. So this is the phasor diagram. In the previous problem where we neglected the resistance, but in this problem we have considered the resistance along with a synchronous reactance also. So on the x-axis we have taken the voltage. For the voltage we have to add the IA area drop parallel to the I. Perpendicular to this one you have to add the IA excess drop. Parallel of these two is nothing but a IA ZS. Now the phasor sum of this one and this gives the E. If there is any disturbances occur, then E becomes a E dash, which giving an angle of 2 degrees. Now the synchronizing power equal to ESY equal to, from this phasor diagram, ESY equal to 2E sin delta del by 2, that is equal to 2 into 7162 into sin delta del is nothing but this angle 2 degrees divided by 2, nothing but you are getting the 1 degree, you are getting the 250 volts. Now the synchronizing current equal to the synchronizing voltage divided by the synchronous impedance, we are getting the 8.324 at angle 87.33 degrees. This current lags this voltage by 87.33 degrees. The same current ISY leads ES by 11 degrees. See from this calculation. So the synchronizing power equal to 3V ISY cos of that angle, that is 11 degree, divided by the 1000, because we want to convert that value to kilowatt. Substitute all the values, you are getting the 155.68 kilowatts. Two similar 400 volts three phase alternators shared equal kilowatt power delivered to balanced three phase 50 kilowatt 0.8 power factor lagging load. If the power factor of the one machine 0.95 lagging, find the power factor and current supplied by the other machine. So in this case, the two generators which are connected in parallel, which is supplying a current of total load power equal to 50 kilowatt, the power factor cos pi equal to 0.8, angle becomes 36.86 degrees. The reactive power of the load, that is equal to P into tan pi, 50 into tan 36.86, 37.5 kVAr. Nothing but a load is consisting this much of reactive power. Now the two generators are equally supplying the power. So the power supplied with each generator equal to 25 kVA. The power factor of the first generator cos pi 1 equal to 0.95, that is given in the problem. So pi 1 equal to 18.2 degrees. So the reactive power supplied to the first generator, that is equal to the power rating, nothing but 25 into tan of 18.2 degrees, it is giving the 8.22 kVAr. The total reactive power is this much, but in this reactive power, the generator 1 is supplying a reactive power of 8.22 kVAr. So the remaining reactive power has to supply by the second generator. So the reactive power supplied by the second generator equal to 37.5 minus 8.22, it gives the 39.28 kVAr. Now the phase angle of the generator 2 equal to tan pi 2 equal to the reactive power supplied by the second generator divided by the power supplied by the second generator, that is equal to 39.28 divided by 25. Pi value are getting the 49.51. Now the power factor of the second generator equal to cos of pi 2 equal to 0.6493. Now the current supplied by the second generator equal to power supplied by the second generator, that is 25 kilovolt divided by root 3 VL power factor, it gives the 55.6 amperes. Power supplied by the second generator, current supplied by the second generator, and power factor of the second generator also. Thank you very much. Keep on watching these videos so that you have a good idea regarding to the electrical machines too.